Hi everyone, I'm Professor Bergasser, and in this video we're going to be talking about how we apply the work-energy theorem to the spring force law. And remember, the spring force law is a restorative law. It always points in the opposite direction in which the spring is either stretched or compressed. So if the spring is stretched, it's going to point inward to bring the spring back to its normal length. And if the spring is compressed, it's going to point outward to push that spring back out to, again, its normal length. And so we've written down a force law here for the spring force. It's proportional to a spring constant, and then it depends on the difference between the stretch or the position of the end of the spring relative to its equilibrium length. Now, in many cases, we can set that equilibrium length or equilibrium position to be the origin of our coordinate system, in which case the force law is very easily written as minus k times the vector or displacement vector from that origin. Now, how do we compute a work for this particular force law? Well, we normally write our work term as the force, in this case the spring force, dot our displacement. But if I write that out, that's equal to minus k times our position vector dot displacement. And we immediately see a problem here because as I'm displacing this spring or displacing an object attached to the spring, the force itself is changing with position. In fact, if we plot this relationship in a graph, so if this is the equilibrium length at the origin, and I'm stretching the spring out in this direction, then the spring force is increasing linearly with that direction, with the slope is equal to k. So if we're actually going to compute the work acting on an object as it's being stretched out, we actually have to compute a lot of little works, which I'm drawing in here as a bunch of rectangles. The total work is just going to be the sum of all these little bits of work that are done as you're moving the spring out to smaller and smaller steps. So this is not correct. We actually have to do a sum over lots of little spring forces here and little displacements as we move this spring across. And of course, this begins to approximate an integral, which is going to be minus k times r times dr, because in this case, the spring force is always going to be acting in the anti-direction, anti-parallel to our displacement. So I can do this integral from some initial position to some final position, and this is a pretty straightforward integral. It's just minus 1/2 times k times r squared, and I'm going to evaluate that at my final and initial positions. So this is the work done by a spring as it is being moved from two different lengths, two different positions. And we should also note that the spring force is a conservative force. So spring force has a potential energy. Any conservative force, which is a force that if we stretch the spring and we bring it back, we're going to be exactly at the same amount of energy at the end of that, we can write down a potential energy term for that, which is just equal to the negative of the work done. And so this is equal to 1/2 k times the difference in positions. And if our initial position is just the unstretched length, then we can set that equal to 0, and we can just write it down as 1/2 k times r squared. So we can approach any of these spring problems by either directly computing the work done, or we can take advantage of this potential energy term, look at the total energy of the system, and as long as there's no other dissipative forces acting, we can solve this problem by using total energy. We're going to see an example of both of those solutions in the next couple slides. So as a first illustration of how we apply our work-energy theorem to a spring problem, let's consider this case where we've got a spring attached to a wall, a horizontal stretch, and then the block attached to the end. And we're going to compress this spring from its natural length by 72 centimeters and then release it from rest. And we want to find out what the maximum speed of the block is as it's sliding out. And for this problem, we're going to ignore friction so that we don't have a dissipative force that we have to worry about. Now there's a couple ways that we can approach this problem. We could do it directly from the work-energy theorem, looking at the work and how that changes the kinetic energy. And we can look at from the concept of total energy as a sum of kinetic and potential energy. So let's look at approach number one first. and that's looking at the work-energy theorem. Work as F dot dr is equal to the change in kinetic energy. To start off, we have to make sure we write down the knowns and the things that we want. So the knowns in this problem include the mass of the block, which is given as 50 grams. That's 0.050 kilograms. We're given the spring constant as 4.0 newtons per meter. We're also given in a displacement, an initial displacement, of 72 centimeters, which is 0.72 meters. And we're also told that at the beginning the object is at rest, the spring is at rest. So we can write down our initial velocity as 0 meters per second, and that also tells us that the initial kinetic energy is equal to 0 joules. So that's an important initial condition to consider. Now what is it that we want to know? Well, what we want is the final velocity, whatever that is, and we have to sort of think about where that final velocity actually occurs. So the question is actually about the maximum speed, and if we think about it as the spring is compressed and it's let go, it's going to accelerate the block because there's a positive force pushing it away from the wall, and that force is going to continue to push outward up until the point when the spring reaches its natural length, its unstretched length. At that point, the spring is going to be stretching and therefore pulling backwards, and so the net force is going to be pulling in the other direction, the opposite direction. So our maximum speed really happens when the spring is at its natural rest length, which happens when it goes from that 72 centimeters compressed back to its 0 centimeters compressed, its natural length. So that means we want VF when the total displacement from its rest position is equal to 0 meters. Okay, so if we're approaching this from the work-energy theorem, it's important to now draw a force diagram so that we can see where the forces are acting and what forces we have to take in consideration in the direction of motion. So let's schematically draw our block attached to our spring. And now let's look at the forces that are acting on this block. The block has a mass, so we've definitely got a weight vector that's added here. And it's in contact with the surface of the horizontal surface, so there's going to be a normal force acting on the block. But because the friction is equal to 0, we've assumed no friction, there's no friction force acting at this contact. And finally we have the spring force, and because the spring is compressed, it's going to be pushing the mass outwards, and so that spring force is acting in this direction, K times R. All right, and we also now have to consider which way the motion of the block is going to go. We've already sort of predicted that it's moving in this direction. So we can actually now compute what are the components of the force that are acting in the direction of motion. Well, from our diagram, it's very clear that the component of motion is really just the spring force itself. So we can write down the work acting on the block as just the spring force. In this case, it's in the same direction, Kr, times delta R. But remember, that spring force is changing with position, so we actually have to use our integrated spring force rule. So that's going to be equal to 1/2 times K times the difference in the positions. And the difference in positions are 0, all right, that's the final position, minus our original delta R squared. So 0 squared minus delta R squared. And again, this is a minus because work is going to be in the opposite direction, the force is acting in the opposite direction of the motion, right? And if you're unsure, you can always look at the point that when we do this, we have a negative number in here, we have a negative out in front, we're doing positive work, and we're accelerating the object, and that makes sense. Okay, so the work is pushing this way, that's all the work terms, and that's equal to the change in kinetic energy, which is the final kinetic energy minus the initial, but the initial is equal to 0 as well. So we're just computing now the final kinetic energy. And that, of course, is equal to 1/2 times mass times the final speed squared. So we can rewrite all these terms. If I cancel out our 1/2 and I divide by m, I'm going to get Vf squared is equal to K over m times delta R squared, or Vf is equal to the square root of K over m times delta R. And when we put in all our numbers, 4 newtons per meter divided by the mass, in fact, let's actually do this so we can check our units, 4.0 newtons per meter, divided by the mass, which is 0.050 kilograms, square root, times our displacement, 0.72 meters. Just to check the units, remember that newtons is equal to kilograms meters per second squared. So we cancel out our kilograms and we cancel out our meters. So we have a square root of 1 over seconds squared, which is 1 over seconds times meters. That's a velocity. And when we write all these numbers together, we end up with an expression of 6.4 meters per second as our maximum speed. Now let's approach the problem from a different perspective, and that's from the perspective of energy conservation. We know the potential energy expression for a spring, and we know there's no dissipative forces acting in this problem. Because we've set the coefficient of friction equal to 0, we don't have that dissipative force that's acting to slow down the object and remove energy from the system. So we can assume that the energy of the system is going to stay constant at every part of its motion, from the beginning to the point where it's got its maximum speed. So let's go ahead and try to apply that theorem. And the way we do this is we write down our initial values and our final values for our kinetic energy and our potential energy. And then we're going to add those together to get the total energy of the system. Well, so our initial kinetic energy, because the object starts at rest, is 0, so that's easy. Our final kinetic energy is an unknown. That's something that we've actually got to solve for. In terms of potential energy, again, if we assume that when the spring is at rest, when it's unstretched, we have 0 potential energy. It's 1/2 k times the stretched or compressed length. Then the initial potential energy is just equal to 1/2 times k times delta r squared. Whereas our final potential energy, if it's at the point where the spring has reached its unstretched length, that's the sort of point where the force drops off to 0, then that's going to be the case where the potential energy is equal to 0. So we can fill in that number as well. All right, now we can just add these numbers together to get the total energy. So that's 1/2 k delta r squared on this term, and our unknown final kinetic energy. And because we have no dissipative forces, we can just set these two terms equal to each other, and now we can go about in solving the problem. Okay, so if we bring back this expression up here, we've got 1/2 k delta r squared is equal to our final kinetic energy, and that's equal to our 1/2 m vf squared. And you can see that we're getting a very similar expression that we had last time. If we cancel our 1/2s and we isolate our final velocity, this is going to be the square root of k over m times delta r, which is exactly the expression we got last time, and so we know that we're going to get the same number. So we've been able to solve this particular problem in two different ways, one applying the work-energy theorem directly, and one looking at energy conservation. And depending on what problem you're working on, either one of these approaches may be useful or easy to use. It's good to sort of consider both those cases whenever you're approaching a problem that involves energy. Now let's see how the energy approach can solve what actually turns out to be a somewhat complicated problem, which seems very simple, and this is a problem we've actually seen before. That's the mass suspended by a spring from a ceiling. Previously we calculated the equilibrium height, the height in which the forces of the spring and the force of weight cancel each other out and the spring is at a fixed position. And we also calculated the period of oscillation and the actual motion of the object about that equilibrium point. But now let's take a look at what happens when we apply an energy approach to look at where the object moves to at different stages. And so we have the same problems. We have the mass is 2.3 kilograms. We have a spring of constant 150 newtons per meter. And we're going to stretch the spring down below its equilibrium length, down to 80 centimeters below the top. And then we're going to release it from rest and see how high it goes as it's moving up. Now, in this case, we can definitely deploy a energy conservation because we have no dissipative forces acting in this problem. And so the energy, which is the sum of the kinetic energy and the potential energy, is going to be constant in this case. But we have to consider actually two forms for potential energy. We have both the spring force, which has its own potential energy term, and the weight force, or the weight potential, which is just mg times the height of the block. The other thing is that we're going to have two kinds of motion happening here, which is actually pretty useful to map out. So let's put my y-axis here pointing downwards, and we measure in meters. We're starting this block at minus 0.8 meters on this diagram. Its original unstretched length is minus 0.3 meters, and we're going to be at some mysterious height above that unstretched length when the block reaches its maximum height. Now, depending on where this block is, we're actually going to have different forces acting on it. So when it's initially starting off here, and up to the point in which it's gone past its equilibrium point, we have the competing forces of weight and spring force acting in opposite directions. At the point where it moves beyond its unstretched length, the string's unstretched length, which is 0.3 meters, in that case then the spring force is going to turn around, and now it's going to be aligned with the weight force. All right. So you can see that if we took this approach from a pure mechanics problem, we'd have to take into consideration this change in force as it moves past this 0.3 centimeter, or 0.3 meters, the unstretched length of the spring, and that could be a somewhat complicated problem. But now let's approach this from an energy perspective and consider just the initial and final end states of our block, the initial end state being where we release it, and the final end state where it reaches whatever its maximum height is. So we can just calculate, or at least write down, some expressions for what the kinetic energy is going to be at both these points, the potential energy due to gravity, and the potential energy due to the spring force. All right, now, we've released it from rest, and so we know that down here at the bottom, the kinetic energy is equal to 0. When it reaches its highest point, that's the point where the spring force has accelerated the object such that it stops, both the spring force, in this case the weight force, so the point that it stops. And so at that point, we've got 0 motion, all right, at its maximum height. Of course, if it had more kinetic energy, it would just keep going. But if it's at its maximum height, it's got 0 velocity, and so the kinetic energy is also 0 at the top of the motion. Now we can write down the potential energies, and that's just mg times the particular positions, which are going to be negative because I'm measuring it down from the ceiling, so this is mg minus 0.8, and here it's mg, and then minus 0.3 plus some extra length, which I'm going to specify here, because in fact that's the length that we want to figure out. How much higher does it go above this unstretched length as the spring is compressed? Okay, and now let's look at the spring potential energy. At this point we are exactly 0.5 meters from its unstretched length, and so this is going to be 1/2 times k times 0.5 meters squared. And for the maximum point, it's gone some distance delta r from its unstretched length, and so that's 1/2 k times delta r squared. So clearly what we want is to figure out what delta r is. Oops, I'm not sure what that symbol is, but we'll just erase it. Okay, so that's the number that we want in this problem. Okay, so we've actually kind of set up our initial final. This is our final state, and this is our initial state. But let's actually write this down as an equation. All right, and these two are, of course, equal to each other, the sum totals of these. So let's just start by just equating these two things together. So I'm going to write the initial side, mg minus 0.8 meters, plus 1/2 k times 0.5 meters squared. And that's going to equal to the final state, which is mg times minus 0.3 meters plus delta r, and then plus 1/2 k times delta r squared. Let's just rearrange this a little bit so that we can get all of our terms on one side. So I'm going to move all of these parts over to the other side and kind of flip it over here. So we've got 1/2 k delta r squared. We've got plus mg times delta r. And then we've got minus 0.3 mg plus 0.8. So that's going to be plus mg times 0.5 meters. And we've got this 1/2 k 0.5 squared, which we're going to move over here, so that's minus 1/2 k times 0.5 meters squared and that's all equal to 0. Now we can get a little clarity at this point by just evaluating some of these numbers out in front. And so if we do that, this is going to be 75 joules per meter squared in front of the delta R squared. For the mg term, we've got 22.6 joules per meter times delta R. And all of these numbers over here add up to minus 7.47 joules is all equal to 0. Now notice the units I've used here. I've gone through a little bit quickly. K is the spring constant measured in newtons per meter, but newtons per meter is also joules per meter squared because a newton is a joule per meter. So that gives us the right units here because we're multiplying by meter squared. The weight is just newtons, but again that's joules per meter, so that's joules per meter times the length is going to give us joules. And when you work out all the numbers here, of course these are both expressions in joules, and we get the right units in here. So everything works out unit-wise. And at this point, this is now just a quadratic expression that we just have to solve with our normal tools. So for example, this is A, this is B, and this is C. Then our expression for delta R is just writing down our grade school expression for quadratic formula, minus B plus or minus B squared minus 4AC. All right, and when you put in all of those numbers here, just straight math, you get out 0.2 meters for this mystery displacement relative to the unstretched length of the spring. So we're almost there because that's not actually the answer. The answer was how high it goes on this y-axis. And of course it's 0.2 above this point. So now we know that the final position is just minus 0.3 plus 0.2, and our final position is here at 10 centimeters below the maximum height of the spring. So again, this could have been a really challenging problem if we had done this from a Newtonian perspective, solvable but challenging. But when we look at it from an energy perspective, the hardest part was just solving a quadratic equation. Everything else was very easy to write down because we know our expressions for potential energy for gravity and spring force. And we didn't have to consider at all the sort of transition between where the forces flipped over, because when we talk about energy, we're only interested in the end states, the initial and the final state. What happens in between, as long as there's no dissipative forces, is irrelevant because all we care about is the energy state at the beginning and the end. So hopefully from these examples you've seen how we can apply two different ways of using the work-energy theorem to actually solving problems involving springs. One is to actually calculate the work-energy theorem, looking at the work as a force acting over a distance and equating that to the change in kinetic energy. And because the spring force changes with distance, we have to actually look at the work term integrated, so that gives us a 1/2 k times the difference in positions, each quantity squared. We can also apply it from an energy conservation perspective because the spring force is a conservative force. It doesn't dissipate energy away. And we can see that that allows us to solve for many relatively complicated problems because all we worry about is the endpoint measurements. So make sure you do some practice in trying these two approaches for various problems, not just spring force, for other forces, and good luck on solving your spring force problems.